so we're going to talk about section R.7, the last section of the review chapter, and we've kind of hit on it a little bit, been mixing in some of this as we went through some of the previous lectures. So if you haven't watched all the lectures, you might want to go back and review some as well. It might help with this too. But the rule is the fractional exponent, whenever you have a base raised to a fractional exponent, that the denominator is the root and the numerator is its exponent. And we, on the last lecture, we had like square roots would be, for example, 49 to the 1/2 power means it's a square root. The 2 is the root. The denominator determines the root. All right, so some examples here. It wants us to practice writing these in the opposite way. Take a radical, write it as an exponent, and then we're going to practice the other way too, just to get the hang of this. So this could be written as 16 is the base. It's understood to be the first power, so it's the 1/4 power. And then we could work that out in either form that's most comfortable for you. The next one, it should have a negative sign in front of it. Say there's like a -1 multiplier on the final answer. But the 16, again, is raised to the 1/4 power. The denominator is the root, and then there's a negative, a weighting negative in front. Let's go ahead and see what this would be. These may not be obvious to you. You might have to think and crunch on your calculator a little bit, but 2 times 2 is 4, 4 times 2 is 8, and then 8 times another 2. That'd be 4 times in 2 by itself 4 times would make 16. So the root here would be 2. A 4th root of 16 is 2. Same answer here, but there's a negative at the end, so it becomes a -2. Next one we would write is -32, and since it's under the radical with it, this negative needs to be in a parenthesis. It's understood to be the first power there, so it's the 1/5 power. Again, these may not be obvious to you, but 2 times 2 times 2, you just guess 2 probably and see how many 2's it takes to get here. But 2 times itself 5 times is 32. So this is a perfect 5th root of 2. And it's also a negative this time because you can't have a negative that's an odd root, because a negative times itself an odd amount of times is actually negative. So we could say not just a weighting negative, but as this number to that power, it's a -2 times itself 5 times is -32. Cube root, this would be 1,000 to the 1/3 power, and that is a perfect cube of 10. 10 times 10 times 10 is 1,000. 6th root, now they're just getting carried away, right? I don't know, you got to type on your calculator a bit, but what times itself 6 times is 64? It's that 2 again, because we were already up to 2 to the 5th was 32, so 32 times itself, twice 32, we're up to 64. So the perfect 6th root of 64 is 2. 2 times 2 times 6 times. And then 729, and that's not one I'm familiar with myself. I kind of had to look at the book myself for that one. But 729 is a perfect root as well. I think it was 3, but I'm double checking that. I lost my page number. But you can be typing on your calculator. It is 3. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 54. And then you just keep on going, multiplying 3 times 3 times 3, 6 times. So it is 2/3. And then lastly, this is saying what can you times by itself 4 times. So 2 times 2 times 2 times 2 is 16. But you can't do -2 times -2 times -2 times -2 and get a -16. Because an even amount of negatives is always positive. So you cannot do an even root of a negative. That will never be real. Not real. Alright, so now in the next example, we're going to practice going the other way, taking it already in exponential form and putting it as a radical. Maybe we won't do all of these, but just to get the swing, you could go do these either direction. They're interchangeable. Oh, one more. Let's do C. Okay, so they wanted us in the directions to write it as a radical, just to practice going both directions with this. So this would be the radical 8. It's a cube root and then squared. So we could work that out because 8 is a perfect cube of 2, and then when you square it, that is 4. Next, the negative is to a 5th root, so that is doable. We can write that as radical of negative 32, and because it's in the parentheses, the negative is actually in the radical. It's a fifth root, and then we're going to take it to the fourth power. So this is real. A negative that's an odd root we can work, and that is actually a root of negative 2. And then when we take it to the fourth power, the negative times itself 4 times actually works out to be positive. So in the end, it is actually a positive answer. This last example has a weighting negative. You know, I call these weighting negatives. It's like a negative one that's multiplied on, and it has to weight because of order of operations. You have to do this exponent first and then multiply. It comes after exponents in our order. So 16 to the 3/4 would be radical of 16, fourth is the root, and 3 is the exponent. 16 is a perfect fourth root of 2. Then we cube that, which is 8. So all of this comes out to be 8, and then that weighting multiplied by negative 1 makes it negative 8 ultimately for the final answer. Now, not everything is a perfect root, so that's not always going to be true for us. Sometimes we'll have to break our radicals up. I'm going to go ahead and get over to that lesson with you now. So, example 6. What if it's not a perfect root, like 175? If we were doing the square root of 175. So we can't just say, oh, the square root of 175 is boom. It is an irrational number, actually. You could get it on your calculator, but that is not the exact answer, mathematical answer we would want. So we'd want to reduce it in its perfect form. So what we can do is we can break 175 apart and call it 25 times, is that 7? Check me out on that. I think it's 25 times 7, yeah, is 175. And then you can do the roots separately. Square root of 25 that is perfect, and 7 will stay in the radical. Reduce the part that is perfect out of it, and that would be the exact mathematical answer. So non-perfect radicals break apart. Try to find, this is a square root, understood to be root 2. Try to find perfect square roots. You may want to list your perfect square roots if that kind of helps you to kind of have a visual and think about 1 squared, 2 squared, 3 squared, 4 squared, and kind of have your list of what you know to be perfect squares and see, do these go into that? All right. Next example. Negative 3 times fifth root of 32. Now I think this one works out perfectly because 32 is a perfect fifth root, so I thought we were on a roll where they weren't all perfect, but it does work out. 2 times 2 times 2 times 2 times 2 is 32, so that one comes out as 2, and then we've got a multiplier in front, sort of like the weighting negative, only it's got a number with it too, to multiply that answer onto for an answer of negative 6. Next example. Now we get to a non-perfect example again. We're going to work on cube roots. That's a y. All right, so think about your perfect cubes now. So you might want to write yourself a list. The perfect square list. Well, what are some cubes? Like 1 times 1 times 1 is 1. It's a perfect every kind of root, but it doesn't help as much when we're trying to find another number. So you really don't need the 1, but just to be thorough, 2 times 2 times 2 is 8. So 8's a perfect cube. 27's a perfect cube. 64, 125. The list goes on, but that just kind of get us started. You could write more if needed. Well, so 81 is not on this list. It is not a perfect cube. So we try to break it down in some way. What on this list will go into 81. So it works out that 27 times 3 is 81. And again, that may require a little multiplying on your calculator to figure that out, but you can do that and think through it till you find a way to break that apart and get something that is perfect, so we're able to reduce that part out at least. Now x to the 5 is not going to be a perfect cube root, but x to the third will be, and x to the 2 would be the leftover. So x5 is the same thing as x3 times x2. We need it to divide by 3 evenly to do those. And then y7, I'm going to call that y6 times y1, and then z to the 6. So to do the exponents, they have to divide evenly by this. So I have to break them apart. We know from our exponent rules that when you have like bases and you're multiplying, so we broke them apart into their factors, you add the exponent. So I needed 3 plus 2 to be this 5. And then on y7, I needed the most I could get that would divide by 3. So the next under 7 would have been 6. 6 divides by 3, and that makes 6 and 1 to get the 7. All right, so for the exponents, they have to divide by the root. Okay, then take out all the perfect parts. The cube root of 27 is 3, because 3 times 3 times 3 is 27. The 3 is going to stay in there. This x to the third, and then the third root. So if you think about it, we could rewrite the cube root of x to the third. Oh, you can't see that's out of your screen, isn't it? Let's talk about the cube root of x to the third. That could also be written as x to the 3 over 3. You know, if you think about what we did on our last exercise, this converts to a fractional exponent. So it's 3 divided by 3. That's the numerator, that's the denominator. So 3 divided by 3 just makes it x to the first whenever you reduce it down. So this divides by that. It brings it out of the radical as regular x. And also, if you think about it algebraically, cubing and cube rooting would undo each other. So they're kind of opposite operations. So they kind of cancel each other out. That's another reason it brings out the x. So that takes care of that. X squared's got to stay in, though. It's not perfect, has no perfect part. Y to the 6. So 6 divided by 3 is going to bring out a y to the second. Again, this divided by that. This would be the numerator. That's the denominator, the index. So that brings that out. There's a 1 left over. Then lastly, z6 was already divisible, so I didn't have to break it apart. z6 divided by 3 makes z to the second. So that's the stuff that's released from the radical that was perfect. Then write the leftover stuff that couldn't be brought out of the radical is a 3x squared and y. And that would be your final answer. As bad as it looks, that is it. All right, let's try that again. All right, example 7. Let's jump down to example C. We've got 2 problems here to work separately, and then we're going to see if we get like radicals, you can combine, add, and subtract like radicals. So we'll see if that happens. But we just reduce each separately like we just practiced here. Actually, this one's on the list. It's a perfect cube, which is 4. Be brought out just like so. But M4, remember these have to divide when we're doing our variable parts. They have to divide by that. So M4, we make M3 times M1. N5 we would make N3 times N2 would be left over. So then we can take M3 comes out as an M, N3 comes out as an N. We'll have a 4, an M, and an N. The leftover stuff is an N squared. Okay, so that's reduced. Then we have to do the same thing to the second problem here. We're doing a cube root of negative 27. We can do that's perfect cube. 27 is on the list of cubes, so that comes out as a negative 3. Don't forget there's also a subtract between them. Then m to the 10th will need to be broken down. 10 does not divide by 3, so we make that m 9, the first number under 10 that's divisible by 3, and 9 and 1 to be equivalent to 10. In 14, I need to drop under 14. The next number under 14 that divides by 3 is 12. In 12 leaves 2 left over, 12 and 2 to make 14. Then I can bring out 9 divided by 3. That brings out an m cubed. 12 divided by 3 is an n4. The leftover is an n squared. And then there's a double negative, makes that plus. Because just so happens both of these are same index, cube roots, n squared. These are like terms. So I can maybe try to combine those. I was going to maybe try to combine those, but for n